All right, let's get going with our session here. We've got our test coming up this Tuesday, so we need a review session to brush up on things. So I'm just going to be working through some practice test questions and pause a little bit so you have an opportunity to see if you can solve it. And of course, for those watching the recording, they can just stop the recording, work on as long as they need to, and then start the recording to see if they got it right. All right, so without further ado, let's go ahead and get rid of these things we don't need here. Don't need that, don't need this. And I'll just get up here some practice test questions. Oh, first thing, I guess I should point out some important things. I've mentioned it before, so that hopefully this is something you're well aware of. But when I go to the learning modules, Module 9, oh, here, let me turn off the video. There we go. I'll shut up. That if I get over here to the activities, now there's a complete list of concept questions. In fact, let's open that up. So I'll load it there, and then I can open it up. And so make sure that you know these, because as that learning module we were just looking at tells you, we're going to select, there's going to be 5 selected from this list. Now you don't know which 5, but it shouldn't matter, but it's only the ones from 1 through through here, 1 through 16, because we've only covered concepts 1 through 16 so far. But there will be 5 of these selected, and each is worth 5 points. So that's 25 points. So that's 1/4 of the exam. And why they're so important is, if you can't explain these concepts, then you're really not getting an important foundation down. Each and every one of these are really important. That's why they made it on the list. And how you learn these is not memorizing them by rote, but by applying them. For example, concept question number 1, you applied this when you did the StatCrunch assignment, because you had to figure out from your histogram, stem, and leaf what the shape was, whether it's skewed or not. From the box plot, you determined if you had outliers. And based on that, you figured out what you should use to measure the center. Your first choice is mean, second choice is median. But you only get to use your first choice if there's no skew or outliers. Otherwise, it's the median. And spread. Your first choice is standard deviation, but you don't get to use it if there's outliers or skew, because it gets distorted by those. Then you have to use your second choice interquartile range, or IQR, and so forth. But these are all the concepts that you have been applying when you've been doing the homework exercises and practice exercises and quizzes. That's how you remember it, by applying them. All right, so be sure and make sure you know those. And of course, that the learning module lets you know that. And so here's the practice exam. Oh, let's see, we've got a question here. And the question, can you hear me? Well, it shows that my voice is being recorded, but perhaps I should ask everybody, could you respond to let me know if you can hear me? Okay, so some are. And so Kevin, I'm looking at your list here, and your microphone isn't set up. I'll have to send that message to him. Let's see. So I'm going to type this in for Kevin. Oh, thanks, Joy. You got him the message. Okay, so let's see, Joy, we won't have, oh, good, you turned the video off. So you gave Kevin the right on, he just needs to get that turned on. Okay, so everybody's hearing, fine. It's just one person needs to get their audio set up. Once they do that, they'll be fine. All right, well, let's continue on here. That you got these practice exams with the solutions, and then after that, you can get the extra practice exam. So notice that the lesson had the first set, the practice exam and solutions. That's the same ones on the tutorial DVD. And the activities has the extra ones. Okay. All right. Just checking the messages there. All right. So, and of course, you're going to find that, and of course, shortly I'll be opening up the learning modules after exam 1. So for those who get the test done, you can get started on the others. You'll always find a module right before a test that has practice exams and things to help you get ready for the exam. So let's see, those were the highlights I wanted to hit there. So let's go ahead and look at some practice questions. Let's see, I will begin with, now where'd they go? Oh, here we go. All right, let's look at this one. Now, here's the scenario. Calvin got a 477 on his math SAT score, and he was teasing Susie with how much better that was than her measly 29 on the ACT math exam. Well, you have to understand, we're comparing two data values that come from completely different populations. They have different centers, different spreads. For the population mean of all SAT math scores is 621 with a standard deviation of 96. Whereas the population mean of all ACT math scores is 21.0 with a standard deviation of 5.3. Now, how in the world are we going to be able to compare these two data values that come from different populations? Is the answer you can't? It's impossible? That's comparing apples and oranges? Or is there a way? And if there is a way, who did better on their exam? Calvin or Susie? Show and explain how you determine this. So let me just give you a moment or two so you can at least think how you would approach this. Probably not going to give you enough time to do it because then we'd just be sitting around most of the time here. Go ahead, think about it. Okay, so hopefully you immediately thought, of course we can do that. That's what z-scores are for. They allow you to z how unusual they are. See, well, turn each of those into a z-score tells us how far away that data value is, either above or below the mean, and the distance is stated in terms of standard deviations. So we can see relative to their populations, their center and spreads, who is farther to the right, farther above the population mean, meaning they did better, and who's farther to the left, who did worse, got lower score. So what we'll do is, let's get this organized. Now, rather than me scroll down and show you the nice work, I want you to show you the process that you would want to do. So I'm going to use my little annotation tool here, summarizing all of this. And this should look familiar to some problems we've done in the past. But for SAT scores, let's just summarize what we know. Well, let's see, the mean, so let me use the symbol for the population mean, is 621. Population standard deviation, so let's use that symbol. And hopefully you are memorizing what these symbols represent, because we're going to be using them this whole term. It's 96. And our data value from this population, that was Calvin's score, That was 477. Oh dear, is he above or below average? Is he below the mean or above? He's below the mean. Oh, well, that's not necessarily good, but maybe it's not too far below. Now for the ACT exam, we see that the population mean is 21.0. That's very different from this one over here. The standard deviation for this population is 5.3. That too is very different from over here. And Susie's score is the one for the ACT exams, and her score was 29. Now, is she above or below average? Oh, she's above. So already you know Susie did better, but let's go ahead and find out exactly how much better, how much worse. So for Calvin, let's do Calvin's z-score. So the z-score, now this is on your, will be on your formula sheet, so you don't have to memorize it. So we'll take his score of 477, subtract the mean of 621, divide by the standard deviation of 96, and better make darn sure we remember to put the parentheses around that. Otherwise, we'll get a really wrong answer if we don't. So let's just go ahead and punch that one in. So we got our 477, subtract 621, divide by the 96. So Calvin is 1.5 standard deviations below the mean. Well, that's not necessarily too good, and here he is bragging. So a negative 1.50. Now let's go ahead and calculate Susie's, which we already know is better because it's above the mean. We're just going to be thorough here. So for her, z-score, once again, I'll write the formula out, just being extra thorough. So that hers was a 29 minus the average of 21, divide by 5.3. So let's see how far above the mean she is. So we got 29, subtract 21. Notice I put the parentheses in there. Oh, she's a little over 1.5 standard deviations above, or 1.51 if we round off. So once again, I probably should emphasize that we do that, and there she is, a positive 1.51. So about as far as Calvin is below the mean, that's how far Susie is above the mean. So that's quite a gap between them. What? 3 standard deviations difference between them. So by far, Susie did much, much better. Okay, so the thing you want to remember about z-scores is this is how you standardize a data value. And one of the benefits about standardizing it, it allows you to compare 2 data sets that come from completely different populations. You can compare them relative to their populations that they came from. All right, so let's go ahead and clear my little scribblings there. Now, if I scroll down, you can see this work being done much more neatly. But I wanted to show you the process just like you would be doing it. Of course, I should also do this, that these, those are normal distributions, by the way, so that we can also include a visual here. because they both come from populations that are normal. So that means when you go 1, 2, 3 standard deviations above and 1, 2, 3 standard deviations below, you pretty much contain the entire normal population. And Calvin was right there, 1.5 standard deviations below, and Susie is way over here. Just to give you an idea, once again, 1, 2, 3 standard deviations difference between them, a long ways away. All right, well, I think we've thoroughly covered that. Not too much more we can do with that one. So let me clear that. And let's see what our next question is. Oh, here we go. A student's math SAT score is at the 75th percentile. What does that tell you? Now, you want to be very specific and clear about this because we're going to be using these a lot. So explain this in terms of what proportion of the population of other exam scores is, either above or below your test score. So I'll give you a second to think that over. In fact, I'm going to draw a picture of this. Make it sink in a little better. So let's suppose that these math SAT scores, they are normally approximately normally distributed. And when you're given a percentile, that's telling you the percentage of the population that is below that data value. So that math SAT score is a data value. Now, in the center, that's the 50th percentile because it's got 50% below. So, 75% is somewhere off here to the right. So imagine that this area to the left is 75% of the population. This data value right here, that would be your 75th percentile. So it's a data value. It's a point on the number line. This would be for your population of data values. So there's a picture that goes with what a percentile is. But you need to be able to say in words, it's proportion of the population that is below to the left. All right, so let's go ahead and clear this drawing and scroll on down so you can see the answer written there. But once again, our minds are really good at remembering pictures. So use the pictures to help you remember. And of course, you can add that 25% of the exam scores would be above it, since 75 are below it. All right, so here, this is something you want to be able to do, is let's suppose these data values are all the exam scores for a math class. So create a stem and leaf display, create a box plot, then answer these questions. Well, altogether, we can enter this data in, and then I'll pause and give you an opportunity to see if you can do the others. So let's press Stat, and one for Edit. Oh, by the way, with the stem and leaf, you don't have to sort the leaves, but I'm going to show you how to sort the data on the calculator, and you'll find filling in your stem and leaf display is a lot easier if you've sorted your list. You don't have to do that. I'm just telling you it's easier. So that's why I want to demonstrate. So let's go ahead and enter our data. I'm going to give you a minute, see if you can, oh, tell you what, before I give you a minute, I'll show you, if you want to, how to sort your data. It's real easy. After you've entered your data in, you press Stat, and see choice number 2 here? That will sort in ascending order. And that's perfect if you're going to make a stem and leaf display. So I can just press 2 to select it. Now I have to tell it which list to sort. So I'll press the second key and 1, since that's where I put my data. And the right parentheses above the 9 key, hit enter. So now when I press Stat and 1 for edit, it's all sorted. So I know that my stems start with 4, and if I scroll to the end, I know that they end with 10 for the 100. So I can put all my stems in, and it says don't split them. So I'm going from 4 through 10, put all my stems in, and then I can go ahead and just put in my leaves, and I'm just from top to bottom, I'm just going from left to right, filling in those leaves. Just try it. I'll give you a minute. Try it and see how much easier that is. Okay, we'll take a look at the stem and leaf, then give you a chance to work on the box plot. So just looking at the stem and leaf, I'll scroll down just enough here. I don't go too far. So do you see, there's the 9, and then you would, going down, you'd have the 6 and 7, and for the 60s, 63, 65, 67. But do you see how much easier it is to line these up? And you do want to be careful to line them up so you don't distort the shape. But it's much easier to do them when you're hopping all over the place. And as you go over here and scroll down, you can see the 70, 70, 71, 75, 78, 79. Then we've got an 82, 84. We're getting near the end here. There's the 88, the 93, 98, 100. And you can see the nice shape. Now, if you're not lining, if you're being really sloppy and lining those up, it's going to be hard for you to see the shape. So try and take a little bit of care, because these are essentially the bars of a histogram. You don't want to distort them, now do you? Of course not. Now, so going back up there, let me give you a moment to see if you remember how to make the box plot. So I have a question here. Why did our homework split the stems, and will we have to do that on our test? Yes, so you will be told which to do. You never have to figure it out. You'll either be told to split the stems or not to split the stems. So you've had practice with both. And why you're told that is because if you do it, what it says to do, you'll have a much easier time seeing the shape. And if you don't follow those instructions, it'll be harder to see the shape. All right, so let's make the box plot. Now, the thing to remember about the box plot is you got to watch for a couple of the pitfalls. For example, I'm going to check the first pitfall. I'm going to press Y equals. Now, probably, if you've already cleared this out once already, it'd be unlikely that you would see more functions being in there. But if you're letting someone borrow your calculator, who knows what they're doing? So you be sure and go in here. If you see any function in there, move your cursor there and press the clear key. You might scroll down, just peace of mind, make sure nothing's hiding down below where you couldn't see it. Now, another pitfall. Press the second key and Y equals. Now, what if, once again, somebody else is using your calculator and more than one plot is turned on? Well, what you would do is you press 4 and turn all the plots off. So now nothing can go wrong. Once again, you press Y equal, clear out any functions. You press second Y equal, getting into stat plots, and then turn all the plots off. Now all we got to do is press second Y equals. You can do plot 1, 2, or 3. I'll just do 1. And let's set it up. Highlight what you want, press enter to select it. On is highlighted, so when I press enter, it turns it on. Hit your down arrow key. Keep pressing the right arrow key until the modified box plot is highlighted. Press enter to select it. Go down here. If you didn't have your list 1 in there, press second and 1. Frequency is always set to 1. This is a nice thing to use to show if there's outliers. And then, of course, the important thing for you to remember is the next 2 keys we press, so your calculator will find a nice viewing window for you. It's zoom and 9 for zoom stat. It just zooms in for you. Then you press the trace key and then your left and right arrow keys, and it easily finds these values for you. Let's see, I had a question. From everyone, no. So I'm not sure what that means. Okay. Okay. So once again, you've got all of those in there. And now you can see you don't have an outlier there. Okay. So we won't have to split. Right. Once again, it will tell you either to split the stems or not to. So just do what it tells you to do. Now what is the shape of this data? Now here's the important question. Are you going to decide on the shape by looking at your box plot, or are you going to decide it by looking at your histogram? So you got these right here. The thing is, don't trust the box plot to tell you the shape. In this particular case, it's not misleading. Notice how the whiskers seem to be very close to the same, and the medians in the center looks very symmetrical. But, the box plot would look like this if you had a uniform distribution, which is not a normal distribution, maybe even bimodal if it were symmetrical. So, you can't trust the box plot. You got to refer to your stem and leaf display to tell you the shape, which is a bell-shaped or normal distribution. So down here you'll see that, yep, the shape is normal. And for outliers, you don't trust the stem and leaf, you trust your box plot. So there's no outliers. So it's bell-shaped, normal distribution, no outliers. That means we have no skew and no outliers. So what do you use to measure the center if you have no skew, no outliers? Why, your first choice, the mean. Now notice that this data is from the entire math class, so this is the entire population of interest. So that's why I'm saying the population mean. And of course, now let's run the 1var stats. So now, there's 3 things you got to be really good at on your calculator for the test. One is the box plot we just did. The second is the descriptive statistics we're going to do next. And the third and final one is the linear regression that we were doing last week. But here, let's press Stat, right arrow for Calc, select 1 for 1var stats, then press the second key and 1 to get list 1 there and hit enter. Now, of course, it's not showing the population mean symbol. It's using X bar because, hey, most of the time we're entering in random samples, not entire populations. but population mean, sample mean are calculated the same way. So the population mean is 75. Now, you need to explain the reason for your choice. Now, this is very similar to what you were doing in the StatCrunch assignment, except I think you found that you had a different scenario. You had to choose a different center for that one. But this one, you get to use the mean. It's our first choice. Hey, why is it our first choice? Because it gets maximum information from the data, much more than the median does. And there's no skew and no outliers. And you might mention, well, what's so bad about that? Well, the mean gets pulled towards the skew and outliers, which distorts its representation of the typical data value. Remember, that's the job of the center, to represent the typical data value. All right, now for the spread. Now be a little more careful this one, because we got the sample standard deviation and the population standard deviation. Which do we use? Well, what's our data? Is our data sample or is our data population? It's a population, so that means you got to use the population standard deviation. Now, if it had been a random sample, we would have used the sample standard deviation. But we're going to be using this one. And so we got the answer right here. So no, you don't have to calculate it by hand, thank goodness. Now, why did we choose it? Well, it's our first choice because it definitely gets maximum information from the data, which makes it a tedious calculation. There's no skew and no outliers because the standard deviation would get distorted by those. And then it wouldn't do as good a job of showing the typical or standard distance a data value deviates from the mean. Or you could say that wouldn't do as good a job of measuring the variability of the data. Okay, so these are what nice, thorough answers would look like. Now, you say, could I have just said, use it because there's no skew, no outliers? That would have been just barely enough to get by. But students who really answer more thoroughly like this, I have a tendency to put a little green plus there. And those green pluses add up to a little bit of extra credit on their exams. So those people who take the time to really show off what they know, we give them a little extra credit for that. But this is definitely a place where you could have really gone the extra mile, as opposed to someone who did just enough to get by, who just said no skew, no outliers. Now, let's suppose everything is going your way. What's your favorite shape in the whole wide world? Why, the bell-shaped normal distribution with no outliers, of course. Why, that means you use the population mean, population standard deviation, and not only do you get to use them, we will tell you what they are equal to. Hey, you couldn't ask for more than that. Why? And you say, well, what can I do with that? Well, for starters, you could use the empirical rule and get the information. The information is essentially a really nice summary of that entire population. Now, after exam one, we're going to learn a lot more of things you can find out when you know these three things. So the empirical rule is just the tip of the iceberg. I recommend making a sketch for this, but let me just give you a moment to see what you can come up with. All right. So for the shape, you make a nice little bell shape. Then you put in the center the 8, and each of those tick marks is 0.5. And then put a number under each of those tick marks. And you should have something like that. And then it's really nice and easy for you to visualize. In fact, let me just draw in my little lines. So if I go 1 standard deviation below and 1 standard deviation above, look at that area. What's that area in between those two lines? You want to remember 68%. So 68% of this normal population is going to be between 7.5 and 8.5. Now let's see. So we were talking about what unit? Inches. Because we're talking about the length of fish from Lake Larry of all places. Okay? So the middle 68% of all fish from Lake Larry are going to be between 7.5 inches long, 8.5 inches long. Well, that's pretty impressive that you were able to know that, but it's only because you knew the shape, center, and spread. And of course, this empirical rule only applies to normal distributions. Now, let's get back to the annotation. Let me clear those. And let's go. Oops, I didn't mean to do that. We're going to do straight line and go 2 standard deviations above, 2 standard deviations below. So in between those, that's the middle 95% of the population. As long as we have this up here, I'm going to shade in out this little right tail and this little left tail. Because if between the lines is 95%, then that means outside of that is 5%. Half of 5% is over here, 2.5%, and the other half is over here. Now, here's our general rule, is that if you're within 2 standard deviations from the mean, so the middle 95% of all these fish are between 7 inches and 9 inches. Those would all be considered typical, usual lengths of fish for this lake. But if you had a fish that was larger than 9 inches, that would be considered unusually large for this lake, because only 2.5% of them are that large. And if you had got one that was less than 7 inches, that would be unusually small, because only 2.5% of all these fish are that small or smaller. Okay. So of all the intervals, this is the most important one that you'll see the most. What separates the typical usual from the unusual. And why are they unusual? Because they deviate so far away from the center. And then if you go 3 standard deviations above, 3 standard deviations below, you pretty much got all, or 99.7%. And that's, so 99.7% of all the fish in Lake Larry are between 6.5 inches, 9.5 inches. Pretty much all of them. So would it be unusual to randomly select a fish from this population and get one that is 9.25 inches? That would be right about there. Well, yes, it would be. That would, because it's more than 2 standard deviations above the mean. Okay, so there's that batch. Now I got another batch here. Give some more practice, because that was a lot of the good stuff before we got to chapter 4. Now let's do some chapter 4 stuff. All right, so here we got the data for the heart rate for 4 patients who took a specified drug dosage of a new medicine. So the idea is, if we know the drug dosage, would we be able to predict the resulting heart rate afterwards? Well, that's what we'll find out. We'll find the equation of the least squares regression line and use our calculator to get it. And it'll give us the values for R and R squared, and we can use that to determine if we would want to use this equation to use the X variable to predict the Y. Okay, so this is the third and final thing you need to know how to do on your calculator. I'm going to give you a moment to see if you can enter that data in and get your equation. Okay, so I'll put my data in. I gotta see if I can, oh, good, it's starting to wake up now. Okay, let me clear my list by highlighting L1 and press clear and enter. Oh, by the way, do any of you have a deleted list like this? I'll make it really bad. They say, oh no, I'm missing some lists. Remember, it's real easy to fix if that ever happens. Press the stat key, press 5 for setup editor, and hit enter to run it. And it should all be fixed now. So you press stat, 1 for edit, you'll see it's all fixed. So I'm going to always put my X data in list 1, my Y data in list 2. Makes life a lot easier for you if you do it that way. And you've got to put it in this exact order because these have to stay matched and paired up with each other. So remember when I showed you how to sort the list? Never do that with this data. You don't want to sort these lists because then they wouldn't be matched and paired up anymore. All right, so we've got that entered in. Now, how did we get the equation? You press the stat key, the right arrow key to highlight calc, and just choice number 4. So we'll select that. Now, if you always put the X data in list 1, the Y data in list 2, you can just hit enter. And you don't have to do what I'm going to do right now. You don't have to do the second one for list 1, then the comma, the second, and then 2 for list 2. But if you don't use list 1 for X and list 2 for Y, you will have to tell which list the X data is in, which list the Y data is in. Oh dear, I don't have the R and R squared. I'll bet you do. But if there's any of you who don't have the R and R squared, this is how you get it. You press the second key and the 0 key, and that gets you in the catalog. Press and hold the down arrow key until you get down to the D's. We're looking for something called diagnostic on. There it is. So get the triangle pointer pointing to it. You press enter to select it, and then you have to press enter again to run it. Now your R and R squared will show up when you run linreg. So let's do it again. Press stat, right arrow for calc, press 4 for linreg. This time I'm just going to hit enter because I can. And you got your R squared and R. So this is what you need to be able to get. Now your job is to interpret it. So you've got Y equals, and you need to replace A with a negative 11.59 plus B, and replace B with 94.79. Now just don't copy this line, and this line. You have to put it all together. So you have the actual equation like you see here. This is what you need to show. And if it doesn't say where to round off, go to the second decimal place. That's our general rule. Now the R, notice that's a negative 0.35. The R squared is a, now R squared can be written as a percentage. R cannot, but R squared is a proportion. So I'm writing it as 11.98%. Now we need to interpret that. Well, as we learned last week, R is between -1, positive. Now this is negative. Is R closer to -1 or is it closer to 0? Much closer to 0. So that means it's a weak negative linear correlation. This R squared tells us 11.98% of the total variation in our Y variable, which is the heart rate, is being predicted by our X variable, the drug dosage. Does that sound like it's explaining a very big chunk of it? No, it doesn't. Because, you know, the closer this is to 100%, the better it is. And it's a long ways from 100%. Think of it this way. Is it closer to 0% or is it closer to 100%? much closer to 0%. So this X variable is not doing a good job of predicting the Y variable. So no, we would not want to use this equation. All right, but this is a good fundamental summary of what you want to be able to do on the exam. Get the equation, the values for R squared and R, and be able to interpret the values for your R and R squared. Now this one's all concept because you see they've already done the work for you. Now this is a rather generic example because they're not telling us what the X and Y variables actually are. But just like in the previous problem, hey, it's all calculated for you. Now here's the question. Would it be all right to plug in the value of 7 for X in this equation, so we can use that to predict what Y will be? And B, would it be all right to use 65 for X, plug that into the equation in order to predict what Y will be? And then C, based on your values for R and R squared, can we use that as proof that the X variable is causing the Y variable to be what it is? Okay. So these are covered in the concept questions. So what we're actually doing here is applying a couple of the concept questions. All right, so with A and B, when you plug in values for X in order to predict Y, you need to stay within the scope of the model. That means stay within the data that you observe. So what are the range of values for X that we observed? We'll just go over here. What was the smallest? What was the largest? So the scope of our model is all X, using X values between 2 and 20. Anything beyond that is extrapolation, or going beyond the scope of the model, and you should not do that because we don't know what happens beyond what we observe. No telling what will happen. Now, 7 is between 2 and 20. It'd be perfectly okay to use that. But 65, that is way beyond values for X we observe. It would be a really bad idea to plug that in. Don't expect it to do a good job of predicting. So no, it's not all right. Now look at our values for R. Is R closer to 0 or positive 1? It's really close to positive 1, so this is a very strong positive linear correlation. Is this closer to 0% or 100%? Really close to 100%. I mean, 95.45% of the total variation in Y is being predicted by X. That's pretty good. In fact, it's so good you might be tempted to say that this is evidence that X is causing Y, but you would be wrong. You can't do that. Why? This is observational data. In order to prove cause, you need to do a controlled experiment, which we will be learning how to do later on. They're actually called randomized, double-blind controlled experiments. But we won't learn how to do those down the road, but those are how you can show cause, but not with observational data. With observational data, the idea is you take a random sample from the past to predict the future. So this is for prediction purposes only. Oh, let's go down here. So this is all the things we're talking about there. So we say, no, correlation does not prove causation. At this point, you haven't explained why yet, so you're not done. We can only say that X is good predicting Y. Don't stop there. You still haven't said why. It isn't until you say because this is observational data. Another way you could explain it is because a strong correlation can be one of three things. X is causing Y, Y is causing X, but usually lurking variables causing X and Y to be what they are. And by happenstance, they're correlated. But you got to explain why, because, and then give your explanation. All right, once again, all the work is done for you. all they're asking you. So see if you, I've done it for a couple of times for you. See if you can translate those. You just heard it. Now you try it on your own. I think you can do it. So hopefully you said that. Okay, let's go on to the next one. All right, so now don't confuse scatter plots and residual plots with each other. A scatter plot is showing you the relationship between the x and y variable, and you're hoping to see a pattern. But a residual plot is essentially you take that line from your scatter plot, tip it over so it's horizontal. So imagine, if you will, a horizontal line here, and that would be your regression line. And then you sort of like put it under a microscope in order to exaggerate the distance the residuals are from it, just so you can see the pattern. And so you can see 3 different patterns, and you're going to answer the questions. Does that particular residual plot violate any of the conditions for an adequate linear model? In other words, is there a problem with that residual plot? And you've got 3 possible answers. It's the same for all of them, saying that no, the plot of residuals is random. There's nothing wrong with this residual plot. Or the answer could be yes, there is a problem. That problem is there's a discernible pattern. Or the problem is yes, there is a problem with this residual plot, and that problem is the residuals do not display constant error variance. Now, this is how you'll be tested on residual plots. You're not expected to make them, but if you're given an obvious one, you can answer this. So pick your choices, and I'll scroll down and show the answers. Okay, you made your choices. Here we go. So notice that, hey, see how around this residual line, see how they're fairly constant throughout? That's constant error variance, or homoscedasticity. That's good. And there's no discernible pattern. This means the conditions are met for the linear model. Great. None of the conditions were violated. But what about on this one? Well, is the you see how you had constant variance here? Is it constant here? No. First you have a lot and then a little. And of course, you at this point would have no idea what's wrong with that. But if you take a second term of statistics, you'll learn that this undermines the very foundation of this statistical method. And of course, that's bad. Okay. And so what's problem here is C. It doesn't have the homoscedasticity. They do not display constant error variance. And then over here on this one, you see a pattern in there. Now, for a scatter plot, you love to see a pattern, but not in a residual plot. That's violating a condition for the adequate linear model. So for 2 and 3 here, for these residual plots, the conditions are not met for the linear model, for this statistical technique we're using. It's when your residual plot looks like this. So that's what you're going to see when we learn statistical methods. You just got introduced to one here, but we're going to be learning lots more later on. But there's always a catch, because we're showing you first choice methods. But in order to use a first choice, conditions have to be met. You know, just like you saw with the center and spread. If you wanted to have the first choice, the condition was no skew, no outliers. Here, the condition is your residual plot has to have this constant error variance and no discernible pattern. Let's see what's next here. Okay, so why don't you go ahead and see if you can make a box plot. Maybe you've had trouble with the last one. Let's see if you're better at it now. And see if you got any outliers. So once again, you need to be good at this on the exam. That's why we're having you do it again. All right. So I'm pressing Y equals. Chances are, since the last box plot, I don't think any of us have been graphing any function, so I don't think we need to worry about that. When I press second Y equals, well, we haven't been using any of the other plots, so plot 1, if that's the last one to use, is the only one that's on. So we can just go ahead and in there. We have less to worry about since we already took care of those pitfalls already. And you haven't done any of these other plots, so this should already be highlighted. You should already have list 1 in there, 1 here, and that there. But can you remember the next 2 keys we press to get a nice viewing window? Zoom, 9 for zoom stat. Now, what do I press next so it's easy to see what these values are? Because if I forget, I'd be doing this. I'm trying to guess at it by using this, but you know what? That's not very good. It's not accurate. You want to press the trace key, and it jumps to those and tells you exactly what those are. So you can see the left whisker is 11. First quartile is 13. So 25% of the data is below that. The median's 19. Half of the data is below, half is above. Third quartile is 26, which is the 75th percentile. So 75% of the data is below it, 25% is above. Right whisker goes to 26, and we got 2 confirmed outliers, 47 and 49. And of course, on the test, you'd be given the number line, and since you can easily see those, you'll be able to sketch your box plot above the number line. And by the way, we never do the box plot on the number line. We always do it above because it's too hard to read the whiskers and the outliers if you do it on the line. Nobody does it on the line. So we've got that. All right, now you've done it once before, but let's make sure you can do it. This time you get to split the stems. Like we said, we will tell you what to do. You just do what we tell you. So split the stems this time. Now you don't have to split, put the leaves in order, but you'll find it's easier if you do. But I'll leave that up to you. Okay, so if you want to follow along, I'll press Stat, and I'm going to sort in ascending order because it makes it so much easier. second 1 for list 1. And then I go back in there. So it's clear to me that the leaves start at the 80s at 8, but we're going to split the stems, so I'll have 2 rows for the 8s. And scroll on down here, and then we'll have the 9. So I'll have 2 rows for the 9s, the lower 90s, the upper 90s. And the largest number is 102, so I'll have a row for the 10. So I'll put all those stems in, and then I'll just go ahead, put in the leaves starting at the top, just going from left to right. Now, which are the lower leaves and which are the upper leaves? Well, you could use your fingers from that. So pull out your fingers, and on your left hand, starting with 0, count. You have 0, 1, 2, 3, 4, and you used up all 5 digits on your left hand. That's why 0 through 4 are the lower leaves. Then continue on to your right hand. Those are the upper leaves. Well, that would be 5, 6, 7, 8, 9. And that's why 5 through 9 is the upper leaves. So that'll keep you from getting confused with 5. Sometimes people will put the 5 in the wrong place. 5 is an upper leaf, not a lower leaf. All right, so let's go ahead so you can see this. So for your lower leaves, you can see up here we got 2 80s, and 81, and 82, and 84, and 84. So that's all the lower leaves. Now then we have the upper leaves, 85, 85, 88, 89. And then the lower 90s, 90, 94. And then the upper 90s, the 95, 98. And the last one is 102. You said, should I do another 10 here? Well, it doesn't really matter one way or the other. We usually stop when we run out of data values. So this is what it looks like, and I think you can see that if you turn your head sideways, looking at this like it were a histogram, and if you line these up nicely, you won't have distorted shape, but definitely right skewed. And I should be saying no suspected outliers. We don't know for sure unless we make a histogram. Hey, since I entered the data, I could easily check that, couldn't I? All I got to do is press second, y equals. Everything's set because I just did a box plot. See, it's all set. I just got to do zoom and 9 for zoom stat. Isn't that easy when you've already done one? Well, we confirmed there's no outliers, but I need to do the box plot to confirm it. Now, what are you going to measure the center with? Well, we can't use the mean because the mean's going to get pulled towards that skew and it won't do a good job of representing the typical data value. So we need to use the median and the interquartile range. Now, they didn't ask, but what are they equal to? Well, let's just do that. Since I entered the data in anyways, this will be super easy if you know how. Press stat, go over to calc, 1 var stats, second 1. So notice the mean is 87.8, whereas the median is 85. So you see how the mean got pulled larger? But the median, 85, is representing the typical data values better. And your interquartile range, that's the third quartile minus the first quartile. So that would be 94 subtract 82. Now that formula would be on your formula sheet, but the interquartile range is 12, and the median is 85. Now I did some extra things there that weren't asked just to show off and show you, you can find out all these other things, and also give you a little more practice with 1 var stats. And the box plot again. Okay, now this time, this data is from a random sample. So enter this into your calculator and get those values. I'm going to give you a moment to do that. Well, I'll tell you what, together we can enter in the data, and then I'll give you a moment to do the job. So let's clear our list and enter our data. Okay, so I'm going to pause here a bit while you go ahead and get the mean, standard deviation, median, interquartile range. Remember, it's a random sample. So remember that when you get your standard deviation. All right, so I'll do it now. I'm going to press Stat, go over to Calc, one for one var stats, second one for list one, hit enter. So your mean, or sample mean, and we'll go round to the second decimal place, 8.92. Now, which standard deviation do I use? The 8.47 or the 8.11? And hopefully you'll say, well, it's a random sample, Larry. You got to use the sample standard deviation, 8.47. See, but an earlier one, we used the population standard deviation. Well, that's because the data was for a population. So once again, it all depends. It tells you what the data is, a sample or a population, and then you use the appropriate standard deviation. And the median, we'll need to scroll down for that, is 7. Now let's see, what was the mean again? So look how much larger the mean is. Why do you suppose the mean would be larger than the median? What could possibly be pulling the mean to the right? And hopefully you're thinking, well, it could be right skew or outliers on the right, but you suspect it's one or the other or both. And our interquartile range is the third quartile minus the first. So that would be 12 minus 2.5. So that would be your interquartile range, like that. And I believe this is the last one. See what you can do with that one. So if you've got any questions, ask away, because we're going to be done here pretty soon. So your formula sheet there's only 2 formulas you need, and they're on your formula sheet when you get your test. One is for the z-score, and the other one is for the interquartile range that we were just doing on a previous problem. That's the third quartile minus the first. So you don't have to memorize those. I mean, they're simple enough you probably could, but you don't need to worry about doing that. So use this equation on this data value to turn this data value into a z-score. And then you're going to interpret that. Now, there's 3 things you need to include in that interpretation. You're going to tell me whether that data value is above or below the mean, how far away it is in terms of standard deviations, and third and finally, whether it is or is not unusual. In other words, is it within 2 standard deviations and not unusual, or is it more than 2 standard deviations away and it is unusual? And then, of course, with the empirical rule, you just need to calculate 2 of these standard deviations below for the lower bound, 2 standard deviations above for the upper bound. I'm going to go ahead and clear this. And let's have you check your work here. So if you did your calculations, be sure and got your parentheses around your 59 minus 56, that you came out with a z-score of a positive 1.2. So you interpret that, your data value is 1.2 standard deviations above the mean, and this is not unusual. So did you see how I gave the three things? I told you whether it's above or below the mean, how far away it is, and whether it's unusual or not. So you be sure and do the same. So 2 of these is 5, so just subtract 5 from here and add 5, and you got your lower bound and upper bound. This is a little mathier way of looking at it, but if you draw a picture, that's a nice simple way to visualize it, like we did on an earlier one. All right, well, we've covered all the types of things you should expect to see on the test. You shouldn't have any surprises. Be sure and do at least one practice test to help you catch any areas you're still having trouble with. All right, so that's it for this week. Until next time.